Okay, welcome. Welcome to this lesson. First, subscribe please and leave a like. Share this video to someone who might find it as useful as you do. So today we are going to learn about Newton's law of gravitation. Okay, so here it is. So Newton's universal law of gravitation says that each body in the universe attracts every other body with a force that is directly proportional to the product of their masses and inversely proportional to the square of their distance. So they're saying it's universal in each body. So what they are implying is that let's say it's you, and let's say this model is you, okay, and this is your friend. Yeah, that's your friend. So what they're saying is that you are constantly attracting each other with a force that is directly proportional to the the yeah, you know what I mean. You are constantly attracting each other according to the gravitational law of what. Let's get rid of this. So mathematically, that law can be represented by F equals G M1 multiplied by M2 divided by R squared. I don't know why this is looking kind of, I'm gonna write it myself. I can write that myself. So it's F equals G M1 M2, excuse my handwriting please, multiplied by the square of the distance. So this R is the distance from the center of the two bodies. Like, let's say this is the sun and this is the earth. So it's the distance from the center of the sun to the center of the earth. That's what we call our R. That's our R. And then this F is just the force. The gravitational force is just the force. It's the force. And the SI unit of force is newtons. And then M1 is the mass of the first body in kg. So this has to be in kg. And M2 is the mass of the second body. Like in this case, M1 will be the mass of the sun. M2 will be the mass of the earth. And lastly, what we have there, it's G. It's called the gravitational constant. So G is equal to I'm gonna type it this time. So yeah, G is equal to 6.67 multiplied by 10 to the power minus 11. So let me write it down for you so that you can see it. It's 6.6 oh my god, it's 6.67 multiplied by 10 to the power minus 11. That's UG. So let's say, for instance, the distance between the center of the sun to the center of the earth, let's say it was 12,000 kilometers. I'm just saying it's not, okay? Let's just say it's 12,000 kilometers, and they are saying calculate the gravitational force between the two. Let's say the sun had a mass of 10 kg, which it does not. You will find it on the formula sheet, the actual mass, and the S, let's say it was 4 kg. It's just an example, okay? Yeah. So you're just gonna say this. You're gonna put the 6.67 times 10 to the power minus 11, okay, multiplied by the mass of the sun, which will be 10 kgs, multiplied by the mass of the earth, which I said it's 4 kg, over the square of the distance between them. I say it's 12,000 kilometers, but the SI unit of distance in physics is meters. So you have to convert this 12,000 kilometers into meters. It's just 12,000 multiplied by 10 to the power 3. So you just add 3 more zeros. And then you will have your final answer in Newton. I don't have my calculator right now, but let's just assume that, well, you will get the answer. Let's just assume that the force is 9,000, I mean 9 million newtons. It's just an assumption, which is not true. Okay, I don't have my calculator with me right now, and yeah, that's pretty much it. And the next thing that is useful is to calculate the gravitational acceleration. You know, the gravitational acceleration on near the earth is 9.8 meters per second squared. So they might ask you to calculate that. So that g is actually equal to g multiplied by m1 over r squared. So this m1 is just, this one is just the mass of that planet, and then g is the gravitational constant, and then r is the distance from the center of the planet. Emphasis on the center, okay? So from the center of the planet to the center of the object. So let's say we had our planet Earth. Okay, it's kind of blue. Let's say this is our Earth, and somewhere in space we had an astronaut. Okay, we had astronaut in black. So that's our astronaut. Okay, so your m1 will be the mass of the, you know, the earth, and r will be the square of the distance from the center of the earth to the position that is specified, like if they say where the astronaut is. So you're just gonna have to add the radius of the earth to the height above the sea level. So that will be your total r, and don't forget to square it. So that's pretty much it for this lesson. I'm gonna continue doing this if you are showing interest. Thank you. Bye.